Our next paper is called Ensemble of Machine Learning Models for an Improved Emotion Recognition. And it's going to be presented by Sergio Pulido.
Yes.
Okay, so let's start. You have 20 minutes.
Okay, thank you very much. Okay, well, my name is Sergio Pulido Castro. The project I'm going to show you guys today is named Ensemble of Machine Learning Models for an Improved Facial Emotion Recognition. I worked on this project with Nubia Palacios, Michel Ballen, Sandra Cancino, Alejandra Rizo, and Juan López. This is a joint collaboration between Escuela Colombiana de Ingeniería Julio Garavito and Corporación Universitaria Minuto de Dios, Uniminuto. This presentation is divided in the following sections. First, an introduction to the subject, then the objectives of our project, the methods we used, the results and analysis we obtained, and finally, conclusions and future works. For the introduction, it is important to note that this project is part of an even bigger project in which we developed a tool for the stimulation of the imitation and recognition of emotions for autism spectrum disorder, or ASD. The three main objectives of this big research was the development of a real-time facial expression recognition algorithm through image processing, which is what I'm going to be talking about today. And the other two objectives were the design of an experimental protocol in order to stimulate facial expression, emotion, and recognition, and the development and implementation of a video game in which facial expression feedback is given to the user. So first, I'm going to talk a little bit about autism spectrum disorder, or ASD. According to the Diagnostic and Statistical Manual of Mental Disorders, DSM-5, ASD is characterized by persistent deficits in communication and social interaction and repetitive and restrictive behavioral patterns. Regarding the prevalence of ASD, approximately 13 out of every 1,000 children are diagnosed with ASD on the world. This based on a study that assessed ASD prevalence in the world from 2014 to 2019. On the other hand, in Colombia, 2.39 out of every 1,000 people were treated for psychological development disorders during 2017. However, it is important to highlight that this figure encompasses the development generalized disorder, and it is not a direct indication of ASD estimates. Okay, regarding emotions and facial expressions, emotions in ASD are characterized by an increased difficulty in emotion recognition and low emotional regulation. On the other hand, Paul Ekman, who is an exponent in the field of the facial expressions of emotions, in 1971 demonstrated emotion universality, which means that it doesn't matter which country are you from or which is your culture, you're going to express emotions the same way. In 1978, Ekman created the facial action coding system FACS, and finally, in 2002, the second edition of FACS was published, and the action units were defined. We can see in the right figure an example of the action units. These are the three main action units that are used to identify and to recognize the facial expression of sadness, for example. The objectives of this work are the following. Our main goal was to create an algorithm that is capable of emotional facial expression recognition in order to help subjects with ASD. To achieve this main goal, we have the following specific goals. First, to design an automatic classification algorithm, which effectiveness is improved by combining different hyperparameters and prediction models. And second, to improve the speed of the algorithm by discriminating irrelevant features in the classification of specific facial expressions. The methods to accomplish these goals are the following. We can see here the general diagram for the facial expression recognition algorithm. First, we acquire the image and we detect faces in it. From these faces, we extract two different sets of features. Gradient-based features and facial landmark-based features. We used all of these features to predict two different sets of emotions and then make a final selection. As you can see below, these are the labels we used for this algorithm, which are happiness, fear, disgust, sadness, surprise, anger, and the neutral expression. Being the first six of these, the six basic emotions. For the image acquisition section, we did this with a 640 per 480 pixel resolution, which is a common resolution in webcams. We chose this resolution because this allowed our algorithm to be universally accessible. To exemplify how the algorithm works, I'm going to be using this image in the following slides to show different steps of the algorithm. For the face detection part, we used the single shot detector algorithm, or SSD, which is a deep learning model algorithm with high speed and accuracy. Because of this, no pre-processing was done during this stage, as this algorithm is capable of detecting faces even in non-ideal light conditions. For the feature extraction, as I told before, we have two sets of features. First, facial landmark features, and second, histogram of oriented gradient features, or HOG features. For the facial landmarks, we used Casemi's algorithm to locate 68 different facial landmarks. However, this algorithm didn't always put all the landmarks in the correct position because of light conditions. To improve this, we used histogram equalization on the grayscale image to improve the localization. And for the histogram of oriented gradients, we located the forehead, front, and cheek through the facial landmarks that we located initially with Casemi's algorithm. For each of these three zones, the oriented gradients were analyzed and the histograms were obtained in order to extract different features. In this table here, we can see a summary of the features that we extracted. We divide them in 5 different groups, which are general features, eye features, brow features, mouth features, and gradient in cheeks, front, and forehead, for a total of 62 features, being 23 of them based on facial landmarks and 39 of them based on gradients. For the facial expression prediction, the training was made through KDEF database, where 70 actors performed the 6 basic facial expressions and the neutral expression. As well, the labels here were divided into sets, as a different model was used for those labels that were harder to differentiate. In that sense, we have in set 1 those labels that were easier to differentiate, which were happiness, disgust, anger, and surprise. And in set 2, we have those that were harder to differentiate, which are sadness and fear. As well, we used the neutral expression in both sets. Then we pass through a feature reduction stage in which the relevance of each of the 62 features was identified through Gini's index. Here, we found out that for set 1, only 18 of the original 62 features were considered relevant, and only 15 of the original features were considered relevant for set 2. It is interesting to note that none of the gradient-based features were considered relevant for set 1, and only 6 of them were considered relevant for set 2. This goes according to theory because, as we can see in the action units, and even when you see another person, it is easier to identify the sadness and fear through the front and the forehead, which isn't always necessarily the case for the other facial expressions. In the results, we obtained the following. We found out that the algorithm that best predicted those labels that corresponded to set 1 was an artificial neural network with 1 hidden layer and 5 neurons, for a final accuracy of 86%. Similarly, we found out that the best model that predicted those emotions in set 2 was a random forest with a minimum of 2 samples per node, 15 depth levels, and 50 trees, for a final accuracy of 79%. In the feature reduction stage, we have the following tables in which we compared the accuracy when we trained the models with all the features and only with the most relevant features. We can see here that for most facial expressions, the accuracy is slightly reduced when we only use the most relevant features. However, this isn't the case for some of them. For example, disgust, happiness, and surprise. Moreover, and more important of this stage, is that we achieved reduced extraction time, as the original extraction time of all the features was of 13.93 milliseconds, and the final extraction time for set 1 was of 0.99 milliseconds, and for set 2 was of 7.96 milliseconds. This means that through feature reduction, it is clear that there is a minimal reduction in prediction accuracy. However, the extraction time greatly improved. The final results can be seen in this confusion matrix, where the accuracy was obtained through the test set of the formed dataset, where we found out that there was a lower accuracy in anger, disgust, and sadness, and a higher accuracy in neutral expression and happiness. Moreover, it is interesting to note that, for example, whenever surprise is not predicted correctly, it is mainly confused with fear. This makes us believe that for future works, it will be interesting to combine different sets of facial expressions in order to improve the accuracy for particular emotions. Our final mean accuracy was of 65.25%, and the average speed was of 17.64 frames per second, which we consider really good for online prediction, as we can see in the following slide. Here we can see one of the multiple interactive tools that we created for the bigger project, in which this avatar is controlled by a user, and the user has to find different facial expressions throughout the map. Whenever he finds one, he has to identify, recognize, and imitate the facial expression. Whenever he imitates the facial expression correctly, he has to carry the corresponding face to its corresponding name, the name of the emotion. Taking into account that this project was made to help children with ASD, we believe that by using a video game to teach them about emotion recognition and imitation, not only it will be easier for them to understand these concepts, but also it will be faster for them to apply these concepts in future interactions. In the conclusions and future works, the facial expression recognition algorithm that we created has an important innovation component. First, because we made use of an ensemble of machine learning models, which allowed for a better accuracy, and also the speed of the algorithm the speed of the algorithm was greatly improved through feature reduction, which in time allowed for a better online recognition. It is important to point out that while the accuracy had minimal reduction, the speed highly improved, as the final prediction speed was approximately 14 times better than the original speed. For future works, the facial expression recognition algorithm can be improved through a series of modifications. First, it is important to explore different label combinations for the creation of the ensemble of models, with the ultimate goal of making this an automatic process. Also, it is important to explore the use of deep learning models by making use of heterogeneous databases that improve the generalization level of the algorithm. However, regarding this aspect, it is important to note that to take into account that this algorithm must prioritize speed, and not all kinds of deep learning models could be used for this particular purpose. As well, it is possible to create our own facial landmarks model in order to focus on the improvement of the location of facial landmarks in images that are specific to the emotional facial expressions. Finally, it is important to explore the use of different features, such as those obtained from the wavelet transform and the co-occurrence matrix. On the other hand, this algorithm can be used in other fields, For example, the well-being of a patient can be improved during different therapies by analyzing their current emotional state. Also, human-robot interactions can be improved, allowing the robot to modulate its responses depending on the emotional state of the person which it is interacting with. And finally, this algorithm could be used in an exciting field, which is the detection of microexpressions. However, this is only possible as long as the acquisition system and the recognition of the algorithm are improved. Thank you so much. Muchas gracias. I will be glad to answer all your questions.
Great, Sergio. Let's give Sergio a virtual applause too. Congratulations. That's a really nice work. A very relevant application. The application of this kind of techniques in the treatment of autism spectrum disorder is very, very interesting. So let's have some time for questions now. If there's any question, please write them in the chat, please. Do you hear me correctly?
Yes.
Yes? Okay. So I have a couple of questions. I was very curious to know about how you actually use this kind of techniques in the treatment. And it was very nice to see the video game you showed, because it makes a clear picture of how the techniques can be used. So this question is already answered. And I was also curious about something you say in the paper. You say that the category surprise somehow showed to be a little bit problematic. Not problematic, but it was the label that didn't show the most important increase in performance.
No.
So I was wondering if you have any
Okay.
Any hypothesis for that.
Yeah. Actually, surprise was easier to differentiate than other facial expressions, mainly because it was clear that when a person opens the mouth and the eyebrows are heightened, it is easy to recognize. It is surprise. However, it is mainly confused with fear because of this. Even when you talk to a person, let's not talk about computers. Even when you talk to a person, it is difficult or if you look at a picture, it is difficult to differentiate between fear and surprise. So I will say that yeah, it is that even if a human can't recognize it properly, for a computer, it's going to be way more problematic. But yeah, what we as a team would like to do in the future, or other research teams could help us with, is exploring these combinations of different emotions. Because if we used a model particularly to differentiate between fear and surprise, maybe our results would be better. So, but this also would decrease the accuracy in other facial expressions. So there's like a balance that we have to take into account here.
Yeah. Okay. Thank you. That was clear. I don't know if there's any other question. Okay, and there was something that I couldn't understand in the paper that maybe you can explain it to me.
Okay.
You mentioned that you cannot use cross validation in your method because since you are combining two models, it's not possible to use cross validation, and I didn't get it. Sorry, but I didn't get it. If you don't mind explaining that.
Yeah, of course. I think I don't have a slide for it, but no matter. Basically, because cross validation bases on doing a prediction first with a test, and then training with a set and testing with another, and then iterating through it. We can't evaluate the scores of all of the models between these two stages. I don't know if I'm being clear. So basically, what we do here is, let me see if I can find the corresponding slide. Yeah, here. Basically, we evaluate which of the two sets of emotions we use through these equations, in which we compare the score from the artificial neural network and the number of trees that selected a particular emotion. And we use the index of the maximum of this to select. So this isn't a process that we could do if we do cross-validation, because it only would give the results for one of the sets, and not the combination that we do here. I don't know if I'm being clear here.
Okay. Yeah. Thank you. We have another question from the audience. Jose Ortiz Bechar says, do you compare with other similar projects like DeepFace?
I haven't. Yeah, I don't. I'm not sure if I have DeepFace here, but we do compare with other research. Let me search for it. Yeah, basically here. We were limited in the sense that we only could compare ourselves with algorithms that also predicted online, did an online prediction. Because if we could do it offline, well, we could use deep learning or any more sophisticated models that that weren't limited by extraction time or training time or prediction time. So by looking at these three algorithms, we can see that our algorithm is one of the best for an online prediction. The only one we found out as a team that was better was this one from Sen in 2018. However, they didn't use neutral expression. So by using less labels, it will be easier for them to predict better. But yeah, it was a little limited, the comparison with other studies.
Okay, I see. Well, that's it, Sergio. Thank you once again for your very nice work and your presentation. Let's give Sergio once again a virtual applause.